The primary purpose of power system protection is to detect faults within the electrical network to ensure the safety, reliability, and efficiency of the power supply. Faults, which can occur due to various reasons such as equipment failure, natural disasters, or human error, pose significant risks to both the infrastructure and the people relying on the power system. By detecting these faults promptly, the protection system can isolate the affected sections, preventing the spread of damage to other parts of the network. This isolation helps in safeguarding expensive equipment like transformers and generators from severe damage, thereby extending their operational life and reducing maintenance costs. Additionally, quick fault detection is crucial for maintaining the stability of the power grid. Unchecked faults can lead to cascading failures, resulting in widespread blackouts and significant economic losses. By ensuring that faults are detected and managed swiftly, power system protection minimizes downtime, ensuring a continuous and reliable power supply to consumers and businesses. This reliability is not only essential for daily operations, but also for meeting regulatory standards that mandate high levels of service quality and safety. Overall, the ability to detect faults effectively is fundamental to the economic and operational efficiency of the power system, as well as to the safety and well-being of the community it serves. Purpose of power system protection is to detect faults or abnormal operating conditions. Relays must be able to evaluate a wide variety of parameters to establish that corrective action is required. The most common parameters which reflect the presence of a fault are the voltages and currents at the terminals of the protected apparatus, or at the appropriate zone boundaries. Occasionally, the relay inputs may also include states open or closed of some contacts or switches. A specific relay, or a protection system, must use the appropriate inputs, process the input signals and determine that a problem exists, and then initiate some action. In general, a relay can be designed to respond to any observable parameter or effect. The fundamental problem in power system protection is to define the quantities that can differentiate between normal and abnormal conditions. This problem of being able to distinguish between normal and abnormal conditions is compounded by the fact that normal in the present sense means that the disturbance is outside the zone of protection. This aspect, which is of the greatest significance in designing a secure relaying system, dominates the design of all protection systems. For example, consider the relay shown in figure. If one were to use the magnitude of a fault current to determine whether some action should be taken, it is clear that a fault on the inside fault F1, or on the outside fault F2, of the zone of protection is electrically the same fault, and it would be impossible to tell the two faults apart based upon the current magnitude alone. Much ingenuity is needed to design relays and protection systems which would be reliable under all the variations to which they are subjected throughout their life. Whether and how a relaying goal is met is dictated by the power system and the transient phenomena it generates following a disturbance. Once it is clear that a relaying task can be performed, the job of designing the hardware to perform the task can be initiated. The field of relaying is almost 100 years old. Ideas on how relaying should be done have evolved over this long period, and the limitations of the relaying process are well understood. As time has gone on, the hardware technology used in building the relays has gone through several major changes. Relays began as electromechanical devices, then progressed to solid-state hardware in the late 1950s, and more recently they are being implemented on microcomputers. We will now examine in general terms the functional operating principles of relays and certain of their design aspects. Detection of faults in general. As faults short circuits occur, currents increase in magnitude, and voltages go down. Besides these magnitude changes of the AC quantities, other changes may occur in one or more of the following parameters: phase angles of current and voltage phasors, harmonic components, active and reactive power, frequency of the power system, etc. Relay operating principles may be based upon detecting these changes and identifying the changes with the possibility that a fault may exist inside its assigned zone of protection. We will divide relays into categories based upon which of these input quantities a particular relay responds. Level detection. This is the simplest of all relay operating principles. As indicated above, fault current magnitudes are almost always greater than the normal load currents that exist in a power system. Consider the motor connected to a 4 kV power system as shown in figure. The full load current for the motor is 245 A, allowing for an emergency overload capability of 25%. A current of 1.25 into 245 equal 306 A or lower should correspond to normal operation. Any current above a set level chosen to be above 306 A by a safety margin in the present example may be taken to mean that a fault, or some other abnormal condition, exists inside the zone of protection of the motor. The relay should be designed to operate and trip the circuit breaker for all currents above the setting, or, if desired, the relay may be connected to sound an alarm, so that an operator can intervene and trip the circuit breaker manually or take other appropriate action. The level above which the relay operates is known as the pickup setting of the relay. For all currents above the pickup, the relay operates, and for currents smaller than the pickup value, the relay takes no action. It is of course possible to arrange the relay to operate for values smaller than the pickup value, and take no action for values above the pickup. An undervoltage relay is an example of such a relay. The operating characteristics of an overcurrent relay can be presented as a plot of the operating time of the relay versus the current in the relay. It is best to normalize the current as a ratio of the actual current to the pickup setting. The operating time for normalized currents less than 1.0 is infinite, while for values greater than 1.0 the relay operates. The actual time for operation will depend upon the design of the relay, and will be discussed further in later chapters. The ideal level detector relay would have a characteristic as shown by the solid line in figure. In practice, the relay characteristic has a less abrupt transition, as shown by the dotted line. Magnitude comparison. This operating principle is based upon the comparison of one or more operating quantities with each other. For example, a current balance relay may compare the current in one circuit with the current in another circuit, which should have equal or proportional magnitudes under normal operating conditions. The relay will operate when the current division in the two circuits varies by a given tolerance. Figure shows two identical parallel lines which are connected to the same bus at either end. One could use a magnitude comparison relay which compares the magnitudes of the two line currents IA and IB. If IA is greater than IB plus is an element of where is an element of is a suitable tolerance, and line B is not open, the relay would declare a fault on line A and trip it.